Factory is a living lab with around 2,000 square meters of test bed, production line test bed with state-of-the-art machines, robots, assembly working places, and also a real production plant which will be shown at the end of the tour. So the SmartFactoryOWL is driven by the Fraunhofer IOSB-INA in Lemgo, together with the OWL University of Applied Sciences, where I'm working. And the Smart Factory is a place where we do applied research. We try to stimulate the transfer of technologies towards the companies, and also where we do the teaching. So the students are actually working with the real machines and robots in their studies. So I think it's quite cool. So this tour, of course, we have plenty of things here, but because we have a conference focusing on industrial communications, this tour will be also focused on the industrial communication, and we will talk about topics like security, digital twin, network convergence, or 5G. This tour will be around 1 hour, and if you have any questions, just please write them down, and we will have times to answer them at the end. All right, so let's go to the first place where we hear about cybersecurity. So we are starting with this topic because typically it's left at the end, so that we decided to speak about it at the beginning because it's becoming more and more important. And we have Henning with us, who will share his view and his works on security. So you'll hear how he and his team is contributing to the security in industrial automation. So Henning.
Yes, thanks, Lukas, for the short introduction. Would like to introduce myself. My name is Henning Kresek. I'm sharing the group of interconnected automation systems here at THOWL in Lemgo. And in the area of cybersecurity, we are heavily cooperating with our colleagues from Fraunhofer IOSB-INA. And what I would like to introduce to you today is a platform, which is a mobile platform used for our training sessions, for instance, also for educational purposes in the area of cybersecurity. First of all, we thought about having something real in that area because it's rather important to show that, for instance, attacking PLCs or something like this has a real impact in the end. And the better you can show it, the more it gets into the mind of the one who's really trained at this platform. And what you can see right here is this small mobile box. It's a portable case which can be carried from one place to the other. We are going for trainings in different companies with that box, but we also use it in our lectures at the university. Both sides work quite good, and what we have in here is a small PLC down here which is controlling the process on the other side, which is an easy process, of course. We have a conveyor belt. We have 2 sensors here, each on every end of the conveyor belt. And the workpiece is always transported back and forth. And what we can do right now is to get into this network infrastructure either via wireless networks or just connecting to the switch as an attacker. And from there, we can run different attacks, which we are then also showing to our trainees. And then, for instance, if we are attacking the Profinet network, we are able that this workpiece just falls down at the end of the conveyor belt because it's no longer stopped. And it means that the process is not working as expected anymore. The question in the end is, why are we doing this? In the first place, we are doing this because in the security area, it's not all about encryption, mathematics, and so on. It's basically a topic of processes. And if you want to run a security system as intended, you always need to consider the human factor. And therefore, it's quite important to show or to bring some awareness into the minds of the humans, that they understand what's possible in that area and how attackers can act, might act. in order to also tune their own reactions if they receive emails. That's far away from this scenario, of course. But if you receive an email and just click on that email attachment without thinking about it, that's already the first problem, and many attacks are started like this. And we are using it, as I said, in order to train people. We have also some other research projects running in that project, in that area, but I don't want to discuss this today with you. And that's all from my part for cybersecurity. That's one of my areas. The other one is digital twin and information modeling, and you will hear me again in a few minutes. So see you later.
So thank you, Henning, for this introduction in the area of security, which, as Henning said, it's just a fraction of the things that are happening here at the SmartFactoryOWL. So now we are going to the next topic, which is also quite important and also quite present in the SmartFactoryOWL. And Mark will tell us a bit about digital twin. He will show also a practical use case of digital twin, how we can apply it in a robot application where a physical asset is running in parallel to the digital twin. So Mark, please tell us a bit more about this topic.
Thank you, Lukas. Hello also from my side, and welcome to our Smart Factory. My name is Mark Riedlinger, and I work for the Big Data Platforms group here at Fraunhofer in Lemgo. And my research topics are robotics and the digital twin. Today, I want to present you one of our demonstrators, the digital twin demonstrator. The demonstrator itself consists of this EGOS robot, the digital twin of the scene, a depth camera over here, 3D printed cubes, and last but not least also a start and stop button. Yes, the original idea of this demonstrator was to evaluate the synchronization capabilities of OPC-UA and how we can integrate it to synchronize the digital twin with the real system. The task of the robot itself is to grasp the cubes that are located at the rear trays, pick them up, and stack them one after the other on the front tray. To do so, the real state of the distribution of the cubes needs to be precisely measured and synchronized with the digital twin. For that, we have installed this Intel RealSense depth camera over here, which captures the real state, and I want to show you that. As you can see, when I move the cubes around, I hope you can see it on the camera. The digital twin directly updates its state, and it's working. But also another benefit of this is I can catch error cases like that when a cube is missing, like for example when it fell off during grasping. I can catch that, warn the user, and tell him to restore a valid state manually. But now let's see how the robot performs in action. The robot automatically detects the state and approaches the largest stack, and then continues with stacking the cubes on the front tray. But also an interesting part of the demonstrator is happening in the background. There, data is being gathered using OPC-UA and an influx database, and it's being brought to this big screen here. For example, on the right-hand side, we have the velocity of the end effector, and it's being updated every second. Also, we see the state the robot currently is in. For example, right now it's stacking the cubes. We can see it here. Well, it's called assembly here in this case on the dashboard, but there's also an inverse task of storing the already stacked cubes back to the rear trays. Also, we can see the individual joint values of the robot and the current forces that are acting on each joint. Now, I want to show you the overall architecture of our demonstrator and data platform behind. On the right side, you can see all the visible and physical assets of this demonstrator, and here on the left side, there is the data processing and computing. Our newest addition to this architecture is the asset administration shell of the robot itself. It's being integrated using a OPC UA server, and for that we use the OPC UA companion specification, OPC UA for asset administration shell. This admin shell is being visualized using our in-house software that we develop. It's called, or it's a part of the software. It's called Digital Twin Portal, and it can be used to visualize data right from the admin shell. This portal is a Node.js web service that supports two different types of admin shells, namely AASX and, as we use it here, OPC UA. And now I want to also demonstrate you how this web portal looks like. I've already opened the corresponding asset administration shell of our robot, and here you can see there are three different types of submodels implemented. First of all, we have the digital nameplate, which serves to precisely identify the robot, its components. For example, we have here the manufacturer, its name, the address, and the serial number of the robot itself. Furthermore, we also have the documentation submodel available, and this brings a lot of benefits to us. For example, having the documentation readily available when the product ships saves money and time, but as well as reducing resource consumption on the manufacturer's side, because I don't have to print a stack of papers that costs money and needs time to ship and so on. And here, for example, we can also directly from our tool visualize the PDF document, and here is the robot, or it's the data sheet of the robot and all of the components the robot consists of. Furthermore, we also have the submodel operational data, which is host of the process data the robot produces. And we can visualize here as we have seen on the Grafana dashboard, we see the individual joint values, and we can also let them update in real time. If we press the play button here, then you can see as the robot moves, those values change. But we also have another feature. We can also draw directly a graph with the values we have selected, and it updates in real time also as the robot moves. Okay, that's it from my side. Thank you for having joined this digital tour through our Smart Factory, and enjoy the rest of it.
Thank you, Mark, for this very interesting presentation and very practical application for the digital twin. So now we will go one step further, and we will see how the digital twin can be used to build a production system. It's here we have, of course, not a big plan, but we made a small version of the whole production system, and we used the digital twin technology to implement skills of production components. So in this case, let's say every production module can express which kind of skills it has, and then whenever in a production process a skill is needed, then of course it can be used. So we want to welcome again Henning, who will tell us a bit about this exciting project. So Henning, you're again the speaker.
Yes, thank you. This time without any introduction, so you know me already. What I would like to introduce here is one of our demonstrators, which was constructed as part of a research project which was called Devicos. It's over already, but as you can see, maybe here on this field there were a lot of companies involved. Not all of them were involved in Devicos, but some of them, and as part of the project we assembled this nice demonstrator, which is a real manufacturing system for fidget spinner. You can see them right here. This fidget spinning devices might be still known to you. This was a hype a few years ago, and at this time in 2018 we decided to build them with this manufacturing system, but right now this hype is already over, I think. What we are doing here is we have a system consisting of altogether 6 different manufacturing stations which are assembling this fidget spinning device, and all of them are set up in a way that they are decentralized, so there's no central PLC as part of the whole thing. Instead, all the different control functions are implemented on a per station level, and the new thing, which was already introduced by Lukas, is that we are all doing skill-based. That means we have also a kind of digital twin of each station, and it's modeled as a skill-based system using OPC-UA. So we are also using OPC-UA for this, and all those stations are able to communicate what they are able to do in the end. And they are consisting, if you go further down here, you have a kind of hierarchy. And if you look into the different levels, you can see that we are here on top on the level of fidget spinner production. So this is the whole system. And if we drill down further, we see that this is one station, and this station consists of substations, and all substations have a specific skill which they are able to publish. And then based on these skills, we can set up the engineering in a completely new way, as compared to the old times where everything was done more on a centralized level. And we can further drill it down even to certain components which have some intelligence on board. Maybe in the future it will be further extended. Right now it's a little bit limited, let's say. And if we go into more details, I don't know if you can drive around the corner and see what's going on here in the system. We can see that there's a real robot arm as one station taking the first part, and then it's turned around as part of the manufacturing process. And in the end, we get out of our fidget spinner out of this thing. And a very interesting topic here is that it's basically an activity of a lot of companies, and everything is working in an interoperable way. So we were able, using OPC-UA, to put everything together from different companies, and everything is working together as intended, which is quite hard sometimes. Here it works because of OPC-UA as the main basis or the main technology. That's one part we can look at. And speaking of the digital twin, we were also able to provide a whole model of the system more in a virtual way, which can be used in the same style as we saw before on the station, which is using graphical representations, but also look into details of each station to see, for instance, running parameters of the operation of the whole system. And I would like to show this to you as well. Maybe Lukas, you can give me a hand with the microphone.
Sure.
Because I need to hold my laptop in a way. So I hope you can see it. What you can see here right now is a virtual representation of the whole demonstrator. This is openly accessible, so if you like, you can also go to that website and take a look into this by yourself. So this would work. And what you can do here is to walk virtually into the demonstrator, into the whole system, and take a look at the different stations you can see right here. And whenever you think you would like to have more details, you can just click on those different topics. Whenever you would like to see some more details, you have additional information here, more or less as a data sheet for this specific station or substation, and here you can get all details you would like to have. So that's already an exact virtual representation, at least with a limited amount of information. It's not modeling all different steps, and you cannot see everything in real time, but it's at least the first step to make it visible to an operator or to maintenance personnel or whatever. And that's already the end of this presentation. So if you have more questions, just get back to me. I'm happy to answer more questions regarding this demonstrator. And have a nice evening to all of you. That was my last contribution.
Thank you, Henning, very much. It was always amazing to see this machine in the work. And if you do the virtual tour, do not expect that you can produce the fidget spinner. If you want to do that, you need to visit us in Lemgo. All right, so that was the last topic about the digital twin. So we have a few more digital twins around in the whole smart factory. However, we will not show them to you right now. So right now we are actually starting with 5G or communication topics, more on higher layers. So right now we will talk about 5G, and we have in the smart factory obviously a campus network. And we have also an expert in 5G who is not only a researcher here at inIT, but also a deputy chair in 5G at CIA. And yeah, welcome, Anna. And I guess you will tell us a bit more about 5G in the smart factory.
Yeah, thank you, Lukas. Hello, everyone. My name is Arne Neumann, and I want to give you some overview about our 5G activities, which we have here in the SmartFactoryOWL, the application of 5G and also our research on it. So we have an installed 5G system here, and the first step we need to do when starting with this activity was applying for a frequency license. Since 5G New Radio operates in license spectrum, we had to apply for such a license. And even we had to contact a federal authority for this. The process was not very time-consuming, not very difficult. That was a first really nice surprise. After that, so the frequency range we use in Germany is from 3.7 to 3.8 gigahertz. And the second thing we need to do is to purchase a system. And actually, we have two systems installed here in the SmartFactoryOWL. So we are also able to do some research on coexistence or cooperation between these systems. And at inIT, at the Institute of the Technical University here, we decided for a concept which has all equipment on premise. So we purchased both the hardware and the software. We have it here. So the CoreNet server of 5G is installed in the server room upstairs. And here on the desktop, you can see the base station, one of the base stations. That's this white box here, a small cell. Another one is under the roof of Smart Factory here. And also the user equipment is partially on the desk here, but also widespread in the factory. So the system vendor is Maxware, and you can see here the dashboard which is provided by this company, which shows the server infrastructure. So this server does not only host the 5G core network, but also virtual machines. This shows some edge cloud capability. And we also have virtual machines running some processes in this edge cloud, like here inIT 5G4i, which is a virtual machine supporting some early results of our research project 5G for Industry. Another view shows the user equipment, like here. So you can see that a couple of user equipments are configured, but only two of them are active at the moment. And on the other screen, on the right-hand side, you can see the dashboard from the 5G for Industry project. So this project aims to support both the long-term planning and the short-term management of ICT infrastructure in the production, which is like a backbone for the factories of the future and supports concepts like edge cloud computing and function virtualization, softwareization. And this dashboard is a first drop of this research. It monitors different kind of resources, network resources as well as computing resources, and even memory resources, volatile and non-volatile. We use it to also get some user experience if the presentation is useful to customers or not. And also some of the data is still preliminary historical data or simulated data. So the project is still going on. And some industrial application which we have is 5G. You can see in the background in the video there. It's a use case for the 5G for Industry project for smart maintenance. So we use a HoloLens to support a maintenance engineer who had to find some errors in the system or in the machine. And the HoloLens captures 3D models and renders the models, is able to detect elements in these models, and so the maintenance engineer can be guided and can also establish a connection to a remote support to be guided from them in a manual way. And with the 5G connection of this HoloLens, it's also possible in case of resource constraints on the lens that we outsource some processes to the edge cloud. That means to the Maxware server, which is directly connected with our 5G core network.
Thank you for the introduction. So we stay with the 5G topic, and we go to Timo, who is working at Fraunhofer, and who will also explain to us a bit about their activities. Especially, I think quite interesting are the precise measurements that they are doing with the very nice equipment, which is quite crucial for wireless communication. So Timo, please explain a few more words about that.
Thank you, Lukas. I'm Timo Sigman, and I'm a research associate at Fraunhofer IOSB-INA in the Department of Wireless Networks. And here in the Smart Factory, we have our own 5G campus network, as Arne before mentioned. And on the left side, there's the campus network. It's a Nokia digital automation cloud system, which means we have the configuration outsourced at Nokia. In Finland, there's a cloud server, and the configuration is done by Nokia Cloud. And we do testing. We test different devices, make interoperability tests. This means different manufacturers and different systems. We are not only testing the campus network, we're also testing the public network, and try to figure out for our customer the best solution. Here in the background we have our 5G monitor. This is developed by Fraunhofer, and there you can see some parameters. The network parameters are on the top, and our system search all networks available in the area, and we have also some performance parameters, and we can actualize this. And we measure the network coverage, because as you probably know, the network coverage increase or decrease strongly the network performance, because as your distance increase, your modulation performs weaker, and the network speed and the latency performs weaker. And we have, for this purpose, a system we can go over. The system is called the 3D positioning system, which means we have an AGV, the automated guided vehicle. This automated guided vehicle drives through our smart factory autonomously. It can draw a map from the building, and with this system we are able, Lucas can help. We are able to move in three-dimensional room. For example, we can move up the lift up to 5 meters in high, and on the lift there's actually a Siemens industrial router, and we can measure the performance with this router, and we can also turn this 360 degree and can move this lift, and we are totally flexible in moving around. And what is special on this device, we have here the opportunity to make tests under real industrial conditions, which means we have multipath propagation of the radio waves, and we have distortions because of high electromagnetic fields. And we are not only testing the industrial rough devices, we are also testing with 5G commercial devices, and we are able to work together with our other departments like IT security and artificial intelligence and assistance systems to build and test the whole 5G ecosystem. If you're more interested in the field of our research, you're highly welcome to visit our website, or maybe visit us in the future here in Lemgo. And I think thank you, Lucas.
Thank you, Timo. And I think what is quite exciting about the system is that you can actually program it to measure the signal strength on different places, and you can do it quite precisely, and then you can repeat those measurements at those places with quite a high precision. I think it's in the range of centimeters or even millimeters.
It is in the vertical direction 1 millimeter, and as Lucas said, you can repeat this measurement and store this data to the database, and can test and can compare the data with different manufacturers.
Yeah, so I think it's a really great system. And so maybe this is right now all about 5G. And now we are going more to the wired communication. So we will talk about the enablers for convergence in the industry. And we have Oliver Alexander with us, who will share with us their ideas and their let's say research activities.
Thank you, Lukas. My name is Oliver Conradi, and I'm a researcher at the Institute for Industrial IT here at Lemgo. I want to highlight a research project that is currently ongoing. Its name is Converged Industrial Networks for Industry 4.0, or short, CINI 4.0. We are focusing on enablers for converged networks in industrial environments. More specifically, we're focusing on technologies such as OPC-UA, time-sensitive networking, and single-pair Ethernet, each but also in combination. These technologies are not new anymore. However, we think that the potential is not fully used and applied, especially in industrial environments. Therefore, we are investigating the possibilities and also the limitations to help the industry to make better and educated decisions whether they should apply it in their production process and/or in their products. The peculiarity of this research project is the close cooperation not only with Fraunhofer IOSB-INA here at Lemgo, but also with two Belgian universities, namely KU Leuven and University of Ghent. Our research institutes are working closely with about 20 companies coming from the industry and from Germany and Belgium. Due to this large community that we built, we can all exchange our knowledge and expectations so we all can shape the outcome of the research project. We as the Research Institute are providing hands-on workshops, learning materials and also lectures to transfer our knowledge. Here at the SmartFactoryOWL we already saw some demonstrators that implement some of these technologies that were created in elder projects but also in ongoing projects. We contribute our knowledge into this research project. Such a demonstrator is right next to us, where Alexander will give us a bit more information.
Thank you, Oliver. Hello, my name is Alexander Bendara. I'm a researcher at Fraunhofer IOSB-INA here in Lemgo, and I work in the working group Industrial Communication and IoT. As Oliver mentioned, the four main topics of CINI 4.0 are converged networks, time-sensitive networks, single-pair Ethernet, and OPC UA. And all of these four topics we have here in this demonstrator. We have a Profinet communication, we have an OPC UA communication, we have a single-pair Ethernet connection, and we have time-sensitive network. We also have different link speeds with 100 Mbit between the switches and the end devices, and we have 1 gigabit between the switches. Also, we use different time-sensitive network technologies as preemption or time-aware shaping. As we can see here, we have 2 frames on the scope. These frames are monitored with a measurement solution called TSN Monitor. It's an FPGA-based solution which is developed here by us at Fraunhofer IOSB-INA in Lemgo. These 2 frames use the same communication class, and we also see that we have some network load that we introduce into the network, as you can see now. And the communication class of the OPC UA frame from the development board and the Profinet traffic is not affected by the net load. So a first impression of the potential of TSN and the 3 other communication technologies. So that's all from my side. Thank you very much. Lukas?
Thank you, Alexander. Thank you, Oliver. And yeah, it was a very short, let's say, insight into this very, as we know, topic topic—convergence in the industry. It's a very relevant topic, and these are, our opinion, the enablers to make these networks more simple and more easy to manage. And of course, still keeping them high performant. Yeah, so right now we are going to the last of our presentations. So this is, let's say, our highlight at the SmartFactoryOWL, which is a real production which has been set up here under the roof of a smart factory. So real production means that we are producing real products that are sold at the end by the producer. So there's a much higher expectation in terms of quality and, of course, the costs that are related to the production. And we have Sasha with us, who is working in a smart factory for a very long time. And yeah, he is one of the main driving forces behind this project, and he will tell us a bit more about it. So I'm looking forward to it.
Yeah, thank you, Lukas. Yeah, warm welcome from my side here in the SmartFactoryOWL in the production area. So we have here in real production, for sure. Our main purpose is test equipments, to have test equipments and test different new technologies if they are feasible, good to build in real machines. And if they have in a very good state, then we can now directly test it here in the shop floor side, also in a real production. And therefore we have a consortium of different manufacturers, for example, Arburg, who's the developer of this machine, and also some some vendors who are for the equipments, for example. And with this strong consortium, we have a product from the vendor Kuna. And these products are coffee cups. And these coffee cups we can also individualize with a logo, for example, and have different logos and texts, but also the color, as you see, can be different. And now it's not producing, but I can also show you how we can laser different texts, for example, and individualize these caps. For us here, this is also a data generator, because if we implement some new software, some new technologies, then we need measurable capabilities. So we need these KPIs, the overall equipment efficiencies, these numbers to check if the new technology is very useful, helpful, or maybe not. And therefore, in the most cases, if this machine or this technology will be implemented in an external factory, then our experts maybe don't get this information very soon, maybe too late for this factory owner. And here we have now a real production where we can make these innovations loops a little bit faster. And therefore we need this data. And that was the first goal, to get this transparency of this machine and the transparency of this data. And therefore we add some devices, for example. We have some boxes, some connectors, because all this machine equipments has different interfaces, different protocols. And the first task is to get all the data in one database, for example, in one platform. And then we can check this data and find optimizations. Here, the next step is to measure all this data. As I said, we can use the existing interfaces, but maybe we need more. Maybe we need more data, maybe from the environment, humidity, for example, air humidity, temperatures, and maybe data from an closed shop. Maybe this production cell is in closed shop. Then we need some additional devices, like this, for example. This is an INA carrier 5G, which is with 5G and also by battery powered. So we can add it as a retrofit device and bring it on a robot, for example. And maybe we can go over here and look inside the robot cell, because this white box we have also added on the robot over there. In the meantime, I will also start the robot, that we can see also the data changing on the screen. On the top of the robot over there, we have this box which generates additional data to the production data. And when we see some movements here, so inside this window, there you can follow how it's the text will be lasered. But in the background, now you see the robot moving. And for maintenance cases, we can follow, for example, on a screen over here, also the data of this robot now. But this data which comes only from this box. For sure we have more data, but I want to show you now the information from this box. Here we have a live stream, so we can not only follow the production data, some peaks in the rotation and in the yeah, for example, acoustic, for example, because maybe you hear it, it's a little bit louder here. And now we can combine the picture with the data. And in the next step, we want to use artificial intelligence to optimize and find anomalies, for example. If something is changing in the process, then we can also look in the past, what was the reason of this problem, but also we can forecast, for example, some problems where we can say, okay, we need predictive maintenance because the robot is maybe driving slower than normal, or maybe we have some in the cables, for example, some anomalies. Okay, when we go a little bit over here along the production, then we have transparency, I said, was the main focus in the first step, to see all the production data, and now in different UIs for the different people. So for the AI experts, we see some data, but also for the machine worker, here we have a different interface, because the machine worker also need the information if we, for example, which KPIs of the machine, or for example, the energy data. This is a small device. We can look also on a bigger device when we go a little bit further. And we see also more equipments of the machine. So there is an air conveyor, and all these devices for sure has this different interfaces. And on the small tablet here, we are mobile. We can go around different machines and see and follow the data. But we have also the possibility to go on the machine interface, or here you can see now the interface where we have all the energy data, for example. And for the retrofit device, we need 5G, for example. Here we need classical field bus devices, and all this data go in an influx database, and we can collect, and now we can do different tasks with this. For example, to make a footprint, an energy footprint, CO2 footprint, for example, of the device, of the machine, but also of the product. And therefore we need all the data, pneumatic, for example, but also electrical energies. And for the people who are working on this machine, they can check if everything is okay. And therefore is transparency the first step. But also it is thinkable that maybe the worker has maybe in the future some virtual colleagues. So here we have also one device which is looks like me, and with this device we are also mobile to check around what is going on. And also there we need Wi-Fi, strong Wi-Fi signals, but also 5G to check all the machine data, to check if something is wrong. So if we get an event of this machine, then the first step is to look what's going around. Can we solve it from remote, or is it maybe necessary that we call some human expert for the different tasks? And the first step maybe can such a robot do in the future, and drive around And therefore, it is also necessary in a factory like this to have very good infrastructures. And I hope you enjoyed this overall tour and have some nice information what we are doing. And back to you.
Thank you, Sasha. So maybe if I can add something. So you saw that we are producing here cups. So I think important is also to mention that these cups are not from plastic, but from some biodegradable materials. So it's eco-friendly, and the idea is also to recycle it here at the Smart Factory and then use it as a material for production. So that was the last station on our tour. So so thank you very much for attending the tour.